Hey guys, we're moving on to graphing trigonometric functions, and I thought I'd just do a quick little video. We're going to do more detail on this in our um, Zoom meeting tomorrow, so I hope you guys can make that. Hopefully you'll have watched this video before the Zoom meeting, so I'll send an email out to that regard. Okay, so let's just jump right into it, and I'm going to share a window with you here that talks about the um, quadrant plane and also the angles as they are. So I'm just going to, you see up here where my arrow is, you've got some cos, sine, and tan. And right now I'm just going to show, if I rotate around the circle, you can see this reference triangle gets created. Now the lines themselves, they seem to change. And if I go all the way to the beginning, that's 1 right there. So that would be the unit circle then, right? So we're looking at the unit circle radius of 1, center at 0, 0. And you'll notice that as we increase the angle, we kind of go from one quadrant to the other. And what I'd like you to do is pay attention to the cos, the sine, and the tan values right at the top there. And you'll notice that right now they're all positive numbers. They're different numbers, of course, but they're positive. And of course, if I go into quadrant 2, what's the only trig function that should be positive there? Well, if you remember your ASTC rule, you'll notice that only the sine value is positive there, whereas the cos and the tangent are negatives. And they're changing numbers and negative numbers, but they're decimal forms. And of course, when I get into quadrant 3, what's the only trig function positive there? Well, that would be tangent. So you can see tangents, they change in number, but they're always positive. And if we go to quadrant 4, then only cosine is positive. So if I click on the quadrants feature, you can see quadrant 1, 2, 3, and 4. And of course, we can just kind of go through that again. So quadrant 1, they're all positive there. Quadrant 2, only the sine value. Quadrant 3, only the tangent value. And in quadrant 4, only the cosine value. And if I throw in angles now, if I click on my angles, I can sort of show these special angles we were talking about. And if I go up to, say, 30 degrees, then you can see at 30 degrees, the sine of 30 degrees is 0.5 or a half. That's one of those special angles. And notice the cosine here. The cosine is 0.866. Now that's actually special. It doesn't look special, but that's actually root 3 over 2. If you use your calculator and work that out, it's root 3 over 2. And if I jump to 60 degrees, you'll notice that it's now 0.5 for cos of 60, but then 0.866 for the sine of 60. And what's interesting, if you go over to quadrant 2, and let's take a look at going to 120 degrees. So notice that the sine of 60 is 0.866, and I go to quadrant 2, it's the same value. If I can just get it right on there. There we go. So now it's 0.866. But notice the cos is now negative 0.5. Whereas over here, it was positive 0.5, roughly. There we go, positive 0.5. And the tangent was 1.732. And now it is, there we go, negative 1.732. So that's important to recognize that the number itself is the same. It's just that it's positive or negative depending on the quadrant that you go into. Okay. And what else can we do? We could do radians, I guess. So if we go pi over 3, that's the same as 30 degrees. And once again, it's 0.5, 0.866. And then, of course, pi over 4. We notice the tangent there is 1. And so where else would the tangent be 1? Well, where else is tangent positive? It would be quadrant 3. So it has to be in quadrant 3. And would have to have the same reference angle as pi over 4. So if I go into quadrant 3 and I add pi over 4, that takes me to 5 pi over 4. And if I just click there, perfect. So now I got the tangent of that many radians is 1. Now you'll notice that in the brackets here, you see this 3.927. If you use your calculator and you do 5 pi divided by 4, then you're going to get this 3.927 radian number. We just tend to work in radians in fractions where they have nice common denominators. It makes the math quite a bit easier for us here. And what if I click that? Oh yeah, I can get rid of that. It's kind of weird. I could throw in the coordinates if I wanted to. Okay. So notice that there's your root 3 over 2.5. There's your root 2 over 2, root 2 over 2. And if you use your calculator and verify these numbers, you'll see they're the same as they were on the reference triangle. So let's get rid of some of this terminology here. Keep it in degrees. Let's get rid of our angles and quadrants. Keep the quadrants. Let's get rid of the coordinates. There we go. Okay, so imagine, let's start our lesson here with talking about the sine value itself. So right now, at 360 degrees, or at 0 degrees, you can notice that the sine value is 0. And of course, as you rotate in a positive direction, so as we rotate the angle upwards, notice that the sine values go from 0, and they're 0.4, now they're 0.5, 0.6. And we're just looking at the green one, the sine one right now. And then we're like 0.7, and it just keeps getting bigger and bigger and bigger and bigger. So what do you think the biggest value would be here? Well, if it's the unit circle, the biggest value would be 1. But it actually doesn't matter on the size of the circle. We'll show you why on the notes here. But if you take the sine of any size circle and you take the sine of 90 degrees, that value is always 1. And the reason for that is sine is defined to be y over r. And at that place, the y value is now the r value. So it wouldn't really matter whether r is 2 or 3 or 4. It would now be 3 over 3 or 4 over 4. And once again, we'll show you this on the other slide just to make, because it's a bit hard maybe to listen to what I'm saying here. But what I want you to focus on is this, what's happening to the sine value. So it gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, and all of a sudden it hits 1. And then it gets smaller and smaller. It's still positive, but it's going 0.9, 0.8, 0.7, 0.6, 0.5, and then all the way down here. Now the sine value is back at 0. So it's actually the same as it was over here. So it's positive, 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 positive. And of course, that's because the y values in these two quadrants is positive. So the sine would have to be positive. And it goes down to quadrant 3. Now it's negative. It's getting even smaller and smaller and smaller. It goes all the way down to -1, and then back to 0. So I'm hoping that kind of shows what's happening to the values of sine as you do a turn, as you do a full circle turn here. So I'm going to go to the slide now that shows my, where is it here? Shows my OneNote, and then we can actually do some writing on this. And I'm just going to really be pretty basic today. I'm not going to get too complex on this. But if I was looking at right here, say I was looking at the graph of y equals the sine of theta, then I'm going to draw a little graph. I'm going to do two graphs actually. One graph I'm going to draw is the one that we have been drawing, and I'm going to, maybe I'll draw this first, and I'll put my circle on top of that. It's about the right size. I'm going to drag it over. So I'm going to sort of plop it right about there. So it's kind of roughly on the graph. And I'm going to work in radians here. I hope we're okay with that. So I'm going to make this 0. I'm going to make this pi over 2. I'm going to make this pi and 3 pi over 2. And then make this 2 pi. And let's think of the unit circle here, and that's going to make our job much easier. So these coordinates here, they're going to be at 1, 0, because remember the unit circle has a radius of 1, center at 0, 0, and on the far side here would be -1, 0, and down here would be 0, -1. So what I'm going to create a little chart for myself here. I'm going to maybe leave yourself a little bit of room. Let's pick theta, and then we'll do sine theta. And I'm going to maybe make my thetas 0, 90, 180, 270, and 360. And I'm also going to take a look at these in radians. So this is still 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if I just look at the unit circle and I look at 0 degrees, that would put us right here, right? So my y value there is 0, and my radius is 1, so I would get 0. So the sine of 0 degrees or 0 should be 0. Sine of pi over 2 now, I'm going to the top of the circle, so I'm going from 1, so we get 1, and then we get 0,
270, I got like negative 360 with 0.
So what does that tell us? Well, if we look at, let's draw some lines here. See, that didn't work. I'll draw a line like that. And then I'm going to draw another line. Looks like this. That's hopefully good enough. Okay. And I'm going to try to approximate midway points here. So I'm going to draw a little line here. I'm going to split that. Let's go to the very end. Okay, right there. I'll split that line in half, which is the middle line, and then let's split that in half. You know, I probably should use a ruler to make this look accurate, but I think that's pretty close there. Okay. Now, what I'm going to do is I'm going to take this point. I'll draw an arrow here. I'm going to take this point right here, and I'm going to make this my theta axis, and my y-axis is going to be the height that I can reach on the circle. So when I go to the sign of 0, I'm at 0. That's that number right there. But when I do the sign of 90 or pi over 2, I'm at 1. So let's make this here pi over 2. Just remember that's 90 degrees there, okay? So when I'm at 90 degrees, my y value is 1. So I'll put a little dot here, okay? And if I go to pi, I'm back over here now. So my y values are 0, so back at the x-intercept. And if I go to 3 pi over 2, well, now I'm down here. And my y value there is negative 1. So negative 1 over 1 would be negative 1. So that's 1, 2, 3, 4. 1, 2, 3, 4. So there's negative 1. So I would be down here. And of course, if I go all the way to 2 pi, I'd be back at the beginning again, which would place us right there. And the wheel would just keep on trucking. Now you might think, well, maybe we just draw lines, you know, connect the dots and get some kind of like kind of shape here. But of course, if you go to pi over 2, actually, let's think of this. If you go to the sign of 30 degrees, think of your special triangle. That's actually 6 down there. 30, 2, 1, root 3. And so the sine of 30 degrees, that would be 1/2. So if you're looking at sine of pi over, sorry, sine of 30 degrees, that's really going to be about here, right? Because pi over 6 would be the same as 30 degrees, and so that's definitely in there. So if I take a look at that, I'm going to be at about 0.5. So you can see that these 3 dots between 0 and pi are not linear. And in fact, the graph has this, it's not parabolic, but I guess you could sort of think it looks kind of parabolic when you graph it. And you get this, this shape here, okay? So what I'm going to do now is I'm going to graph the cos graph. Now, before I do that, though, I should probably just point out, think of a wheel turning, and someone says, well, as the wheel turns, and someone says, what's happening to the y values? Well, the y values would initially get bigger because they're going up, 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 up. And as you pass, they're going down. So they're going down, down, down. And then they kind of keep going down, 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 down until you get to the very bottom, and then you go back up. And if you look at this curve, that's kind of what you did. You kind of went, you know, up, 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 up in the beginning, and then you kind of went down, 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 down to 3 pi over 2, and then you went back up again. So that's sine. The reason you want to think of it that way is sine is defined to be y over r. So you're curious about what is the y value doing as you do that. So let's graph the cos graph on the same grid, and then we can make some observations, and we'll just stop there. It's a really quick little video here. So I'm going to look at now the graph of y. I'll use a different color here. Let's use purple. How about purple's a nice color. So let's say y equals cos of theta. Okay. And I'm going to use the same concept here. I'm going to use sort of concept mapping. So I'm going to use theta, and I'm going to use cosine of theta. And let's go for 0, pi over 2, which is 90, don't forget. Pi is 180. 3 pi over 2 is 270. And 2 pi, we'll be back at the beginning again. So just draw maybe little lines here. Okay, so if I take the cos of 0, I'm at the start there, and you notice that at the start, your x values here are 1. So you'd have 1 over 1, which gives me 1. And of course, at pi over 2, I'm up at the top, which gives me 0 over 1, which is 0. And then the cosine of pi, I'd be way over here. On the far side, I get negative 1 over 1, which is negative 1. And if I go to 3 pi over 2, I'm down at the bottom. So that's going to be 0 over 1, which is 0. And back at the beginning again, I'd be 1 over 1, which is 1. And now if I plot these points, you'll see the graphs actually are somewhat similar, but there's differences here. The cos of 0 is 1. The cos of pi over 2 is actually 0. Cos of pi is negative 1. Cos of 3 pi over 2 is 0. And the cos of 2 pi would be the same as the cos of 0. And once again, if you plug these numbers in, like for example, the cosine of 60 degrees is actually half, so that would be about here. And what you would get is this similar shape where it kind of curves down, 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 curving back up, and then back up kind of like that. So the purple graph is the cos graph, and the green graph is the sine graph. The green graph is the sine graph. I'm not sure why I'm so particular about colors, but just to distinguish between the two of them. Now, this type of curve that we're going to discuss here is referred to as a sinusoidal curve. And although the word sine is in here, the sine and cosine graph are actually the same graph. They're just, if you think about chapter 1, it's actually just been translated left or right, depending which graph you're looking at, a certain number of units. So I guess you could almost argue that the sine graph is the cos graph if you moved it pi over 2 to the right. So if you took the purple graph and moved everything pi over 2 to the right, or moved it 90 degrees, so it's kind of out of phase by about 90 degrees. So that's kind of weird. That's kind of strange here. Now, just two other words we're going to come across, and then I'm going to kind of just stop the video. The other thing I was going to mention was two words. One is amplitude, and the other is period. And the amplitude of the graph is basically kind of how, I can think of it as how high up it goes, but it's measured from the middle of the graph. So I'm going to call this line along the x-axis, at least for this graph, I'm going to call that sort of the middle place. And I'm going to refer to it as a midline. I don't think that's the actual terminology, but maybe for our purposes, we can think of it as the midline. And what you'll notice if you were on the midline, say you were on the midline looking up at the purple graph, you would say that, well, the highest possible value would be at this point, or maybe the point on the other side. And the lowest possible value from that midline would be this value. And you notice that on the cos graph, that value is 1. So it has an amplitude of 1. So we're going to say the amplitude here is 1 for the cos. So I'll use purple for the cos. So it has an amplitude of 1. Now, if you look at the sine graph also, if you were on the midline looking up, the highest point on the sine graph would be right there. And that's a distance of 1. That would be 0, of course. And from here down, that would also be 1. Now, you might say it's -1, like displacement and stuff, if you're thinking about displacements, but distance-wise, it's 1 unit in value. So really, the sine and the cos graph both have amplitudes of 1, at least in these two pictures. And we'll show we can change that. You can alter the amplitude of a sine graph or a cos graph quite easily. And then the period of the function is defined to be the time or how long it takes for the graph to repeat itself. So imagine a wheel spinning, and so you imagine you got on right at 0 degrees. How far or how much would you have to turn in order for you to repeat the pattern again? So you basically repeat what you've done. Well, once you go around 360 or once you go past 2 pi, you're going to be repeating the pattern again of what you went through. So if you were on the sine graph, I'll just sort of sketch over this, you'd be going up, 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 and then down, 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 and then down, 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 and then up, 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 up. And then after 2 pi, you would go back up again, and it would repeat what you just saw from the beginning. So how long did that take to do? Well, in this graph, it took 2 pi or 360. So 2 pi or maybe 360 degrees. And that would be for the sine graph. Now the cos graph, it's not really any different. You're just kind of looking at the x values, and this is a little harder to visualize, but imagine you were right here in the beginning. Well, your x value right there is as far to the right as it can be. Like that's the biggest x value you can be right there. So this is why the cos graph starts at the highest value. And then as the wheel turns, as it's turning, as it goes upwards, what's happening to the x values, not the y values, but what's happening to the x values as you go upwards? Well, as the wheel turns, the x values are getting smaller. They're actually getting shorter. And of course, when you get to pi over 2, now the x values are at 0. And if you keep turning, the x values just keep getting smaller and smaller. They get more and more negative, and then they get to the bottom. But once you're at the bottom here, once you start turning back, you start to go back up again. And, oh, I'm sorry, once you're over here, sorry, they're gonna keep going down. And keep going up, 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 up. And once you're at the top now, what do you think is going to happen after you pass 2 pi? Well, once you're at 2 pi, you're basically going to repeat the pattern again. So it's going to go down, 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 down again. So the cos graph also has a period of 2 pi or 360 degrees. And so tomorrow's lesson, we're going to talk about how we can alter the amplitude in the period. But what I wanted to show you today was what a sinusoidal function look like. And so sine graphs and cos graphs are really indistinguishable. You could write an equation for what looks like a cos graph as a sine graph and what looks like a sine graph as a cos graph. So there's really no change here. Now, I didn't look at tan today. You might want to think about tan. Tan would be a strange one because tan is y over x. You might want to think about what's happening to the y and the x values as you rotate. It's easier to think about cos and sine because those ratios are y over r and x over r. And of course, r is the radius. So for a circle, the radius isn't going to change. It's always the same number. Let me just give you an example of a question I mentioned on the other slide we were looking at. If I said the sine of 90 degrees, and let's say you're on this wheel, and let's say the radius is 10, okay? And we said unit circle was 1. Let's make it 13. That's just such an unlucky number, right? So someone says, what's the sine of 13? Well, the sine of any value is y over r. So if the radius is r, then the r value would be 13 because that's what we said the radius was. But what would your y value be at 90 degrees? Well, if you're at 90 degrees, you're here, and you'd be right up there. Now, of course, if you run a line from the center of the circle to that point, well, that would be the radius of the circle, which is 13. So that is 13 over 13, which is 1. So we're just trying to show you that, or I'm just trying to show you there, that it doesn't really matter whether the circle is, a small circle or a big circle or a medium-sized circle, just the one that's just right, that its sine of 90 degrees would always be 1. And the sine of 180 would always be 0, and the sine of 270 would always be -1. So it doesn't matter how big or how small the circle is, the value of the sine of a specific angle will always be a fixed value. So tomorrow, once again, we're going to go over more on amplitude period and on the sine and cos, but I would encourage you to do that. Another thing I might get you to just check out tonight, just to see if you can graph this on your own, is going to a website called Desmos. And I think I talked about this in class when we were looking at the polynomial functions, but I might be wrong. A lot of things have happened since then. So I'm going to switch my sharing here, and I'm going to go to, hopefully this will work. Let's see here. Okay, so if I go to Desmos here, I can't seem to get rid of that writing now. That's cool. Annotation. Oh, I never knew I could do that. Maybe I can erase that. Let's get rid of that. Wow, look at that. You can almost draw a car. That's pretty cool. Okay, so let's close all these things down. Annotation. Okay, so let's take a look at our equations. Let's go y equals sine of x. Okay, so my scale is kind of weird here, so I might want to go over here. So I'm going to it just changed that for you. And my y values, I'm going to make them, let's make them a bit bigger. Let's go from -1, that's -13, -1 to 1. Okay, that's pretty good. So I can actually, let's make my x value -2 pi. Okay. And then let's work in, this is the step. This is what the lines you see on the bottom are. So I'm going to make my values here pi divided by 2. So every step is pi over 2. And then I'm going to work in radians, and I'm going to close this down now. Screen there. Okay, so there's what the sine graph would look like. And I can go type in now cos graph. So y equals the cosine of x. Cosine of x. There we go. And so you get this kind of cool picture. And of course, you can do other weird things. You can stick numbers in here if you want. I don't know, like 2s and maybe 0.5. And you get weird shapes, stuff like that. And so I would encourage you to play around with those numbers. And that'll give you some kind of understanding what's happening to the period and to the amplitude of these functions. So I hope that works for you. And I'm going to stop the video now. So I hope you guys have a good night, and we will talk to you tomorrow.